This is Dr. D. Govardhan, Professor in Department of Aeronautical Engineering, Institute of Aeronautical Engineering, Hyderabad. The topic is problems on moment of inertia of standard sections and composite sections. Okay, in order to solve certain problems, we require the fundamentals of area of moment of inertia of standard sections. Like the mass area moment of inertia of rectangle about the central axis, I-axis and I-y is represented as now I-axis is equal to BDQ by 12, I-y is equal to dBQ by 12, and the area moment of inertia about its base is represented as IAB, which is equal to BDQ by 3 now. Similarly, for hollow rectangle, the area moment of inertia of hollow rectangle is equal to the difference of moment of inertia of outer rectangle and cutout rectangle. Let capital B and capital D is representing base and depth of outer rectangle, and lowercase letter b and d is representing the breadth as well as the depth of cutout rectangle. Then I-axis is equal to capital BD cube minus lowercase bd cube divided by 12. Similarly, IY is equal to capital DB cube minus lowercase letter dB cube by 12. For the triangle, the moment of inertia about its central axis, which is parallel to AB, is given by BH cube by 36, and the moment of inertia about the base AB is given by BH cube by 12 now. The circle, since the circle is symmetrically about the central axis, x-axis and y-axis, hence I-axis is equal to I-y, which is equal to pi d to the power of 4 by 64. That means where d is equal to diameter of the circle, which is also equal to pi r to the power of 4 by 4 now. The moment of inertia of hollow circle, it is also symmetrically about the x-axis and y-axis and passing through the centroid. Hence, I-axis is equal to I-y, which is equal to pi by 64 into capital D to the power of 4 minus small d to the power of 4, where capital D is representing the diameter of the outer circle and small d is representing the diameter of the cutout circle. The mass moment of inertia of composite sections. While solving the problems related to composite section, first identify the composite figure to divide into regular segments such as rectangle, square, triangle, circle, semicircle, and so on. After dividing, just identify the reference axis. The reference axis is always one is an horizontal, which should be passed through the bottom of the figure, bottom of the section, and the vertical axis is always passed through the extreme left of the figure and perpendicular to the x-axis. But sometimes, if it is symmetrical about the y-axis, that is vertical lines, that axis is taken as reference lines to determine the position of the centroid. Similarly, if the object is symmetrical about the x-axis, now the x-axis is treated as one of the reference lines to avoid the calculation of determining the position of the centroid, because it lies on the same line, that is yc is equal to treated as 0 now. Now let us find the moment of inertia of composite section. Here the composite section is nothing but here L section we have taken. It consists of two rectangles here represented in the figure 1 and 2 now. This L section is divided into two rectangles in such a way that it has to get only not more than two that is reduce the minimum number of regular figures. That is, we can divide it into in the form of like if it is A, B, C and D like this, and the remaining figure now is E, F, G and H like this. That is, this is treated as one figure now. Otherwise, we can take this nothing but one triangle is nothing but represented A, B, C, D. One more is represented as now E, C, G, H and so on. So divide this composite figure in such a way that it has to contain minimum number of regular sections. The regular section means it is in the form of rectangle, square, triangle, circle and semicircle and so on. And it determine the CG of the section. Afterwards, by using the principle of moment of inertia transfer formula, transfer the moment of inertia of each section about the central axis. Then the total moment of inertia possessed by the composite section is equal to the sum of the moment of inertia of the segments 1 and 2 about the same axis. So this procedure we have to follow to determine the moment of inertia of composite section. Here the problem is find the moment of inertia of the central axis, x-axis and y-axis of the angle section shown in figure. First, to find the center of gravity of the section. Since the section is not at all symmetrical about the vertical axis or horizontal axis, hence the line which is passing through the bottom of the figure is treated as the x-axis now. The line which is perpendicular to the x-axis and passes through extreme left of the section, that is, this is treated as a vertical line. It is known as the y-axis now. With respect to the reference axis, x-axis and y-axis, determine the position of the center of gravity now. So, first I am dividing the figure in such a way that the first section consists of A, B, C, D now, one rectangle. The second one is D, E, F, G and so on. Now let the area of the first rectangle is equal to A1, which is equal to 100 by 20, which is equal to 2000 mm square now. And the position of x1, that is with respect to y-axis, the position of the centroid is equal to half of the width now, that is 20 by 2, which is equal to 10 mm. Similarly, the position of y coordinate the centroid is given by this half of the height now, that is equal to 50 mm. That is 100 by 2 is equal to 50 mm. Similarly, for the second rectangle, for the second, x1 is equal to, we can take it as the thickness is given 20 plus, here the remaining length is 60 by 2, which is equal to 50 mm. Similarly, y2 is equal to 20 by 2, it is equal to, y2 is equal to 20 by 2, it is equal to 10 mm. Area is equal to, that is A2, it is equal to 60 by 20, it is equal to 1200 mm square now. Okay, these are the values for the second segment of the composite section, that is also in the form of rectangle. Then the center of gravity of the composite section is obtained by using the relations yc is equal to a1y1 plus a2y2 divided by a1 plus a2, where yc is representing the position of the centroid of the composite section, a1 is representing the area of the triangle, area of the rectangle 1, And y1 is representing the position of the centroid, already we determined. A2 is equal to area of the second rectangle, and y2 is the position of its centroid with respect to the reference axis x and y now. So, on substituting the values of a1, y1, a2, y2 in the equations, we got yc is equal to 35 mm. That yc is nothing but the position of the centroid with respect to the x-axis. It is at a distance of 35 mm. Similarly, the x coordinate is up here now. That is xc is equal to a1 x1 plus a2 x2 divided by a1 plus a2. So a1 is equal to 2000 into 10 now, and a2 x2 is equal to 1200 into 50 divided by 2000 plus 1200. On simplification, we got this value is equal to 25 mm. That means at a distance from the y-axis, it is equal to 25 mm. That is the coordinates are now 25 and 35 now. These are the centroid of a given L section. Here, if we observe, the centroid is not at all lies within the object. It is treated as the imaginary point at which that entire area of the object assumed to be concentrated. So, it is having the distance of, it is there, already we identified it is equal to 25 and 35 mm. Now, first determine the moment of inertia of rectangle 1 now. About an axis, is passing through its center and parallel to the x-axis now. Passing through its centroid. That is moment of inertia of the rectangle 1 about an axis passing through its center of gravity and parallel to the x-axis. This is known as x-axis. It is known as y-axis. Passing through center, that is at a distance of 50 mm now. That is somewhere. This is known as 15 mm. It is equal to, since it is dividing the height into two parts now, which is equal to 20 into 100 cube by 12. It is equal to, which is equal to 1.667 into 10 to the power of 6 mm to the power of 4 now. The distance between the center of gravity of the entire composite section and center of gravity of the rectangle 1, it is equal to, since 50 minus 35, it is equal to 15 mm, because this side is given 35 mm, this side is given 50 mm now. So the difference value is equal to 15 mm. According to the Parallax Theorem, the moment of inertia of rectangle 1 about the x-axis, it is given by Ix1, that is moment of inertia of rectangle 1 about the reference lines xx. First rectangle Ix1 is equal to Igx1, that is moment of inertia of the first rectangle about its own central axis, plus area multiplied by the square of the distance between the two parallel lines now. That is Igx1 is equal to, already we determined 1.667. Area of the rectangle is equal to, already we determined this value is equal to 2000 into 15. The distance between them is equal to 15 square. That is 2000 into 15 square. This value is equal to 2.117 into 10 to the power of 6 mm to the power of 4 now. Similarly, the moment of inertia of whole section about the y-axis required. The second it is there, the second now. For the second one now, the area is equal to 60 into 20, that is 1200 mm square now. The centroid lies at a distance of 25, 35 here now. For this one, it goes 10 only, it is required now. So, H2 is equal to, we are having 35 minus 10 is equal to 25 mm. That is, Hx2 is equal to 35 minus 25 mm. So, according to the Parallax Theorem, the moment of inertia of rectangle 2 about the x-axis line is given by Ix is equal to Igx2 plus A1 Hx2 whole square, A1 A2 H2 x square, where Igx2 is equal to moment of inertia of the rectangle about its own central axis. Since dividing 20 into two parts, this is equal to 60 into 20 cube divided by 12, which is equal to 0.04 into 10 to the power of 6 now. And hxt is the distance between the centroid of the composite section to the centroid of the section 2 now, which is equal to 35 minus 10 is equal to 25 mm. So according to the Parallax Theorem, Ixxt is equal to Igx2 plus A2 H2 x square, which is equal to 0.04 into 10 to the power of 6 plus area is equal to 100, distance is equal to 25 whole square, which is equal to 0.79 into 10 to the power of 6 mm to the power of 4 now. Now the moment of inertia of entire section about the x-axis is given by the sum of the moment of inertia possessed by the section 1 and section 2 about that axis, which is equal to 2.2117 into 10 to the power of 6 plus 0.79 into 10 to the power of 6, which is equal to 2.907 into 10 to the power of 6 mm to the power of 4. This is the answer for the moment of inertia about the x-axis. Now the moment of inertia about the y-axis is required. So again I am representing the position of the central axis now, which is central axis is nothing but passing through the year 25 and 35 there. About the y-axis required, that means nothing but we have to move toward the left hand side, that is the x coordinates we required. So here now Iy1 is equal to, we are having Ig(y1) plus A1 Hy1 square now. Here it is required, this is equal to, where Ig1 is representing the moment of inertia of section 1 about the y reference axis. Ig is representing the moment of inertia about the y axis, but passing through the central axis of element 1, which is equal to, since it is dividing 20 into 2 parts now here, which is equal to 100 into 20 cube divided by 12, equal to 0.67 into 10 to the power of 6 mm to the power of 4 now. The distance between the centroid of first element and the centroid of whole section, just moving toward the right hand side, which is equal to 25 minus 10, which is equal to 15 mm now. So Iy1 is equal to Ig(y1) plus A1 Hy1 whole square, which is equal to 0.67 into 10 to the power of 6 plus 2000 into 15 square, which is equal to 0.517 into 10 to the power of 6 mm to the power of 4. The moment of inertia of the rectangle 2 about the y-axis is given by Iy2 is equal to Ig(y2) plus A1 Hy2 square now, which is equal to, where Ig(y2) is representing the moment of inertia of the rectangle 2 about the central axis, but parallel to the y-axis. Since parallel to the y-axis is nothing but it is dividing 60 into 2 parts, hence it is equal to 20 into 60 cube divided by 12, which is equal to 0.36 into 10 to the power of 6 mm to the power of 4 now. Similarly, the distance between the centroid of whole section and the centroid of section 2 is equal to 50 minus 25 is equal to 25 mm. So according to the Parallax Theorem, Iy2 is equal to Ig(y2) plus A2 H2 Hy2 square now, which is equal to 0.36 10 to the power of 6 plus A2 is equal to 1200 into distance is given 25 square now, and calculation we got 1.11 into 10 to the power of 6 mm to the power of 4 now. The moment of inertia of entire section about the y-axis is equal to the sum of the moment of inertia possessed by the first and second rectangles about the y-axis, which is given by 0.517 into 10 to the power of 6 plus 1.11 into 10 to the power of 6, which is equal to 1.627 into 10 to the power of 6 mm to the power of 4. Now find the moment of inertia of a T section with a flange of 150 mm by 50 mm and wave as 150 by 50 mm about the x-axis and the y-axis through the center of gravity of the section. Find the moment of inertia of a T section is given. Here it is given the dimensions is equal to 150 by 50 mm web and one more is given 150 by 50 and so on. Both are having equal now. Now first divide that segment into two parts now. Here it is treated as a one rectangle now and another one is treated as the second rectangle like this now. It is there now. And if you observe this object clearly, it is representing this object is symmetrically about the vertical axis now. Hence, represent this vertical axis as one of the reference line. The line which is passing through the bottom of the figure like this, it is treated as the x-axis and it is treated as the y-axis. Here the symmetrical line y-axis when we are taking, it is not required to calculate the x-coordinate of the centroid because the x-coordinate of the centroid always lies on vertical lines. Hence, here xc is equal to 0 now. Now yc is equal to, we have to require a1 y1 plus a2 y2 divided by a1 plus a2. That means for the composite figure, first of all, we have to determine the position of the centroid because our problem is to find the moment of inertia of a T section about the x-axis and y-axis which are passing through the center of gravity of the section now. Okay, now we have to determine the area of the first section. That is, the area of the first section is given by 150 by 50. Area of the second section is equal to again 150 by 50. The constant both are. And y1 is equal to representing the position of the centroid of the first section with respect to the x-axis now. But here it lies where it now in the middle point of 50 mm now. This distance is equal to 150 plus 25. It is equal to 175. That means y1 is equal to, we can take it as 150 plus 50 by 2. It is equal to 175 mm now. Similarly, y2 is equal to, that is the position of the centroid for the second section is equal to, it is the half of 150 by 2 with respect to the x-axis now. It is equal to 75 mm. And substituting these values in the equations, yc is equal to a1 y1 plus a2 y2 divided by a1 plus a2. We got the position of the centroid is equal to, that is 125 mm. That is, it lies at a distance of 125 mm from the base like this now. This is known as the position of the centroid. Assume it is represented as IGG now. That is at a distance of 125 mm like this with respect to the x-axis and it is known as the y-axis now. The moment of inertia of the first rectangle about the central axis we required. So first of all, determine the position of, that is mass area moment of inertia of the rectangle one about its central axis parallel to the x-axis section figure now. It is given by IG1 which is equal to, since 50 mm is dividing, which is equal to 150 into 50 cube divided by 12 now. Here this is the treated as here now H1 which is equal to the, that is the distance between the centroid of the first element to the centroid of the composite section. Here composite section is given at a distance of 125. Hence H1 is equal to, we can take it as 175 minus 125 which is equal to 50 mm now. So by using the fundamentals of Ix1 is equal to Igx1 plus A1 Hx1 whole square, that is parallel to the x-axis, which is equal to the, we given just H1x is equal to 50 mm already determined. Gx1 is equal to 150 into 50 cube by 12. It is equal to 1.5625 into 10 to the power of 6 mm to the power of 4. So Ixx1 is equal to Igx1 plus A1 Hx1 whole square. By using this equation, we got to 20.3125 into 10 to the power of 6 mm to the power of 4 now. Similarly, for this second rectangle, Here it is 125 there from the height. The center of this one is equal to, it is at a distance of 75. So this is called H2 now. H2 is equal to 125 minus 75. Again it is equal to 50 mm now. So Ix is equal to Igx2 plus A2 H2 x square. Igx2 is equal to moment of inertia of rectangle 2 about the parallel axis passing through its center of gravity. Since while drawing these lines, it is dividing 150 into two parts now. Hence it is equal to 50 into 150 cube divided by 12, which is equal to 14.0625 into 10 to the power of 6 mm to the power of 4 now. H2 is equal to, already at 12, just is equal to 125 minus 75 is equal to 50 mm now. The moment of inertia of rectangle 2 about the central axis of composite section is given by Ix is equal to Igx2 plus A1 A2 Hx2 whole square. From this one, 14.0625 into 10 to the power of 6 plus 7500 into 50 square, which is equal to 32.8125 into 10 to the power of 6 mm to the power of 4. The moment of inertia of whole section about the x-axis is given by the moment of inertia possessed by the sum of the moment of inertia possessed by the first section, second section about the central axis, which is equal to 20.3125 into 10 to the power of 6 plus 32.8125 into 10 to the power of 6, which is equal to 53.125 into 10 to the power of 6 mm to the power of 4. This is our required answer. Similarly, the moment of inertia about the y-axis, here it is given y-axis and x-axis now. Here the coordinates of x3 is equal to, x1 is equal to 0, x2 is also equal to 0, x3 also equal to 0 because the centroid lies on y-axis, and moreover it is a symmetrical lines. For the rectangle 1 and 2, the x coordinate of the centroids are x1 is equal to 0, x2 is equal to 0, x is equal to 0. That means hx1 is equal to 0 now becomes hx2 is equal to also equal to 0. That is the distance between the parallel lines and passing through the centroid which are parallel to the y-axis. It should be equal to 0 now. Hence, here h1 is equal to 0 we are taking, h2 also equal to 0. The moment of inertia of the rectangle 2 is equal to, given by about the y-axis equal to, when you are taking y-axis nothing but 50 mm is dividing into, it is equal to 150 into 50 cube by 12, it is equal to 1.5625 into 10 to the power of 4. Similarly, for the rectangle 1 now, 150 mm is dividing now, it is 50 into 150 cube by 12, which is equal to 14.0625 into 10 to the power of 6 mm to square now. Since the centroid of first element, second element and the entire composite sections are in the same plane, according to the Parallax Theorem, the moment of inertia possessed by the entire composite section about the y-axis is equal to the sum of the moment of inertia possessed by the first section and the second section, because they are not at all separated by any distance, which is equal to Iy is equal to 14.0625 into 10 to the power of 6 plus 1.5625 10 to the power of 6, which is equal to 15.625 into 10 to the power of 6 mm to the power of 4. Here for the I section now. An I section is made up of 3 rectangles as shown in figure. Find the moment of inertia of the section about the horizontal axis passing through the center of gravity of the section now. Here, according to this figure now, this I section is divided into 3 segments now, and represented as rectangle 1, rectangle 2 and rectangle 3 now. On examining this figure, it is symmetrical about the vertical axis. Hence, the vertical axis is treated as one of the reference lines. It is represented as a 0, O, Y now. And the bottom of the figure, which is passing through the object, is treated as a x axis now. Now, let us first find the center of gravity of the I section now. Since it is divided into 3 segments, the equation is now, since symmetrical about the y-axis, x coordinate is equal to 0, just y is the coordinate we have to determine now. So yc is equal to, according to the equation, a1y1 plus a2y2 plus a3y3 divided by a1 plus a2 plus and a3 now. So in this case, a1 is representing the area of the first rectangle, y1 is representing the position of the centroid of first rectangle with respect to the bottom of the figure, that is x. This is nothing but equal to how much it is now? Total is given 20 plus 100, 120 plus by 2, that is equal to 30, 130 mm now. That is y1 is equal to 20 plus 100 plus 20 by 2, it is equal to. Area of the first rectangle is equal to 60 into 20 is equal to 1200 mm square now. Similarly, for the second, height is given 20 mm, that 100 mm, and width is given 20 mm. Again, it is equal to 2000 mm square, area is equal to, and height is equal to the position of the centroid. It lies at a distance of 50 mm within this one, but from the bottom, 20 plus 50, it is equal to 70 mm. That is a 20 plus 100 by 2, it is equal to 70 mm. For the rectangle 3 now, 100 into 20, it is equal to 2000 mm square now. Y3 is equal to 20 by 2 is equal to 10 mm. Now substituting all these equations in yc is equal to a1 y1 plus a2 y2 plus a3 y3 divided by a1 plus a2 plus a3. We got 60.8 is the position of the centroid for the I section now. The moment of inertia of rectangle 1 now, here we are taking now, it lies at a distance of 60.8, that is here I am erasing this position now, 60.8, that is 30, it is given 20 and 40, somewhere it is given, this is the position of the GG, it is at the distance of 60.8 now. This distance is given 10 mm and it is given 50, 70 mm. The centroid of the second one now, that is y2, y1 is equal to 10 mm, y3 and y2 is given now, this is given, how much is it? 20 plus 100 plus 10, that is equal to y1 is equal to, we taken 130 mm. So the distance between the central gravity of the composite section and first one, that is h1 y, it is equal to the difference of 130 minus 60.8 now. Similarly, h2y, second one, 70 minus 60.81. h3y, it is equal to 60.8 minus of that 10 values. Okay, these are the values we have to take, h1y, h2y, as well as the h3y and so on. Now, moment of inertia of first rectangle about the x-axis is given by ix1 is equal to igx1 plus a1 hx1 whole square. Already I told gx1 is equal to 60 into 20 cube by 12, which is equal to 40 into 10 to the power of 3, and x2 is equal to 130 minus 60.8 is equal to 69.2 now. Similarly, for the rectangle 2 now, is given, when we are transferring the moment of inertia of first rectangle about the central axis of the composite section, according to the ix1 is equal to igx1 plus a1 hx1 whole square, 40 into 10 to the power of 3 plus 1200 into 69.2 whole square, we got to 5786 into 10 to the power of 3 mm to the power of 4 now. For the second one, ixx is equal to igx2 plus a2 hx2 whole square. The igx2 is representing the moment of inertia of the rectangle about its central axis, which is equal to 20 into 100 cube by 12 is equal to 1666.7 into 10 to the power of 3 mm to the power of 4, and hx is equal to 70 minus 60.8, which is equal to 9.2, and ixx2 is equal to igx2 plus a1 hx2 whole square, according to the principle 1667.7 into 10 to the power of 3 plus 2000 into 9.2, which is equal to 1836 into 10 to the power of 3 mm to the power of 4. Similarly, the moment of inertia of third rectangle about an axis passing through the central gravity of the composite figure is given by ixx3 is equal to igx3 plus a3 hx3 whole square. Ijx3 is equal to, since the rectangle is there like this, it is a parallel, is a 20 mm is dividing. This is 3, 20, it is given 60, and so it is equal to 100 into, sorry, it is given 100. So 100 into 20 cube by 12, which is equal to 66.7 into 10 to the power 3 mm to the power 4. The distance between central gravity of rectangle 3 and the x-axis is given by 60.8 into minus 10 is equal to 50.8 mm. So moment of inertia of rectangle third about the central axis of the entire figure is obtained according to the Parallax Theorem. Ix3 is equal to Igx3 plus A3 Hx3 whole square, which is equal to 66.7 into 10 to the power 3 plus 200 into H square is equal to 50.8 whole square. The total value is equal to 5228 into 10 to the power 3 mm to the power 4 now. So the moment of inertia of the whole section is equal to the sum of the moment of inertia possessed by segments 1, 2, 3 is about the central axis, which is equal to 5786 into 10 to the power 3 plus 1836 into 10 to the power 3 plus 5228 into 10 to the power 3. The total now becomes 12,850 into 10 to the power 3 mm to the power 4. This is our required answer now. The mass moment of inertia of a body with respect to the reference axis is the product of the mass and the square of the distance between the reference axis and the central gravity of the given object. Here, according to the problem now, let us represent a body which is represented this in a plane, xy coordinate plane as shown in figure now. Here IM is representing the mass moment of inertia of the given object. According to the principle, the mass moment of inertia is the product of mass of the body and the distance between the and the square of the distance between the reference axis to the central gravity of the given object. So when we are representing with respect to the Ox and Oy, the moment of inertia of the center of this element, assume it is represented here x and y, and m is representing the mass of the element. Then the moment of inertia of this body about the x-axis is given by mass into square of the distance. Square is nothing but here y now. That is, it can be written as now m into y square now. Similarly, the mass moment of inertia of the body about the y-axis generally represented as the IMYY or simply IYY is equal to m into x square, because the distance is given, it is equal to x now. So here the moment of inertia is the product of mass and the square of the distance between the central gravity of the body from the reference axis. The Parallax Theorem. Generally, Parallax Theorem is useful to transfer the moment of inertia possessed by the object to the other reference lines, which is a parallel to the central axis. According to the Parallax Theorem, the moment of inertia of a given object about a line AB is equal to the sum of the moment of inertia of the body about an axis which is passing through the central axis and parallel to the AB, and the area multiplied with the square of the distance between the lines GG and AB now. That means mathematically IAB is equal to IGG plus MYC square, where IAB is representing mass moment of inertia of the body about a line AB, IGG is representing mass moment of the body about its central axis, M is representing the mass of the body, Y is representing the distance between the parallel lines AB and GG now. So according to the Parallax Theorem, IAB is equal to, we can represent it as IG plus M y c square now. The mass moment of inertia of a uniform thin rod now. So let us consider AB the rod of uniform thickness having length is equal to L now. Let YY is representing the reference axis which is the perpendicular to the axis as shown in the figure now. Here we have to determine the moment of inertia of uniform rod about the lines YY now. Now let us consider small strip of length dx at a distance of x as shown in figure now. Let L is representing the length of the rod now and M is representing the mass of the rod per unit length now. So the mass possessed by the dx length of rod is equal to, that is the here dm, which is equal to the, we can take it as now m into dx now. So the moment of inertia possessed by this small element about the vertical axis yy is given by the product of mass into square of the distance between them now. So mass is equal to m into dx. The distance is given x, hence it is equal to mass of the strip into x square, m dx into x square, which is equal to mx square into dx now. The moment of inertia of the whole length of the rod about a reference length yy is obtained by integrating these equations, which is represented here now, from 0 to length of the rod now. So which is equal to Iyy is equal to 0 to L mx square into dx, which is equal to mx square by 3, 0 to L, the limits ml cube by 3, where m is representing, small m is representing the mass of the rod per unit length and L is representing length of the rod, hence m into L is equal to total mass. The remaining terms is equal to L square by 3 now. ml square by 3 is representing the mass moment of inertia of the rod about the its end perpendicular to the axis now. Now moment of inertia of a rectangular plate now. Here let us consider a rectangular plate having breadth is equal to b, depth is equal to d, and uniform thickness t, and rho b is representing the density of the materials. Now let us consider a small strip which is at a distance of y from the reference axis. This reference axis taken, one is the which is passing through the bottom of the figure, one is just it is passing through the extreme left of the object and perpendicular to the x-axis. So let us consider the strip which is having thickness is equal to dy at a distance of y from the reference axis as shown in figure now. Now the area of the strip is equal to dA is equal to, we can take it as b into dy now. Since it is a three-dimensional object having thickness is equal to t now, the volume possessed by this segment is equal to, we can take it as the area multiplied by the thickness now. The mass is equal to dm is equal to rho, that is nothing but representing the density of the materials, multiplied by the volume t, b, d, y and so on. Hence, the moment of inertia possessed by this elementary mass about the x-axis is equal to I dm is equal to di is equal to mass multiplied by the square of the distance between them, which is equal to dm into y square now. So here we represent now mass of the element is called density and volume of the element, rho into area and thickness of the element, rho into b dy into t, rho t b dy, we got it now. Similarly, the moment of inertia of the element about the x-axis is equal to mass of the element multiplied by the square of the distance, which is equal to mass is equal to rho b t dy into square of the distance equal to y square, which is equal to rho TB y square dy. This is the answer now. Then the moment of inertia possessed by that entire object about the x-axis is obtained by doing the integration from 0 to d now. So we got it now. Ix is equal to the moment of inertia possessed by that entire object about the x-axis is equal to rho t 0 to d b y square dy. Rho t be the constant y square dy. Limits from 0 to d integration now. Okay, on simplification we got which is equal to md square by 3. This is our required answer now. Similarly, IOA is equal to, we can written as now mb square by 3 now. The moment of inertia of this rectangular plate about the central axis here, which is nothing but midpoint of depth, is obtained by using Parallax Theorem. That is IAB is equal to, we are having IG plus mass into square of the distance is equal to, distance is given how much it is t by 2, that is d square by 4 now, which is equal to IG is equal to, we can take it as IAB minus of md square by 4 now. So from this equation we got to IAB is equal to, already we got it md square by 3 minus md square by 4. By using the relationship we got to the moment of inertia of the rectangular plate about its central gravity is given by md square by 12. Similarly, the moment of inertia of a circular section, here let us consider a circle is represented as ABCD or the diametrical axis as shown in figure, having uniform thickness as shown in figure like this. It is having uniform thickness like this. It is there now. Now T is representing uniform thickness. Now consider a elementary ring at a distance of r from the center of the circular plate at a distance of r, having thickness is equal to dr now. The area of the ring is given by 2 pi r into dr, it is equal to dA values now. The value is nothing but equal to dV is equal to area multiplied by the thickness now, that is a T into 2 pi r dr now. So mass is equal to dm is equal to rho into T into 2 pi r dr now. Then here the diameter to axis is nothing but the axis which is passing through the centroids, that is x-axis and y-axis. Since it is equally divided, both are symmetrical about the x-axis and y-axis, hence the moment of inertia of circular plate about the x-axis is also equal to the moment of inertia possessed by that mass about the y-axis now. But here we are taking the moment of inertia about an axis which is passing through the centroid and perpendicular to the base, that is IZZ we are taking now. So IZZ is equal to, according to the formula, it is equal to mass multiplied by the square of the distance. Here mass is given rho t into 2 pi into dr into, that is di is equal to dm into we required r square now. That is according to the formula Iz is equal to rho t, it is given mass is equal to rho t 2 pi r dr into r square rho t 2 pi r cube dr now. This is the moment of inertia possessed by the small ring about the z-axis now. So the total moment of inertia of whole section about the z-axis is given by Izz is equal to, integrating above the equation from the limits from 0 to capital R, that is 0 to r is equal to rho t 2 pi r cube dr, which is equal to rho t 2 pi 0 to r cube dr, which is equal to rho t 2 pi r to the power of 4 by 4, which is equal to Iz is equal to md square by 8 now. Similarly, but IMM is equal to IZZ is equal to IXS plus IYY, and moreover IXS is equal to IYY since it is equally dividing Z-axis and Y-axis, X-axis and Y-axis. Hence, we can take IX is equal to IYY, which is equal to IZZ by 2, which is equal to MD square by 16 now. Okay, moment of inertia of triangular section. Consider triangular section ABC as shown in figure, having uniform thickness T now. Here it is given like this. Having T is representing uniform thickness T now, B is representing the length of the base, and H is representing height of the triangle now. Now, in order to determine the mass moment of inertia of rectangular plate about the base BC, let us consider strip PQ at a distance of y as shown in figure, which is having thickness dy now. So, the area of the strip is equal to, small area is equal to, we can take it as, let the length of the PQ is represented as now, here B1 now. That is equal to B1 into dy value. But the triangles ABC and APQ both are similar triangles. The length of the corresponding sides, the ratio of length of the corresponding sides is always equal. That means PQ divided by BC is equal to H minus Y. This distance is equal to H minus Y. Total distance is equal to H is given. That is H minus Y by H. Or PQ is equal to B into H minus Y by H. Or which is equal to, we can take it as B by H into H minus Y. The area of the strip is equal to PQ into dy. That is PQ is equal to B by H into H minus Y into dy now. The moment of inertia of that entire section about the line BC is obtained by the product of mass multiplied by the square of the distance between the lines, which is equal to area is given, area is equal to B1 dy, which is equal to B into B by H into H minus Y into dy. And when we are multiplying thickness, it gives the volume. Again, when multiplying the density, it gives the mass of the body. Square of the distance is equal to y square. That is rho T B into H minus Y into H dy y square. And simplification we got to rho T B divided by H minus Y into y square dy. Again rho T into B by H. And in simplification we got to Hy square dy minus y cube dy. In order to determine the mass moment of inertia possessed by the entire triangular section about the base BC is obtained integrating above the equation from the limits 0 to h now. That is the total mass moment of inertia is obtained rho T into B by H integrating from 0 to h, Hy square dy minus y cube by dy, which is equal to rho T B by H into Hy cube by 3 minus y cube by 4. Here LCM is the 12. We got rho T into B by H 4h square minus 3h square by 12, which is equal to rho T BH cube by 12. Since rho T BH by 12, when we are taking rho is the density, T is the thickness, area is equal to half into base into height. We are simplifying this equation by taking here it is equal to this one and h square by here 6 we are taking 12 is nothing but 2, 1 is there and 6 now, which is equal to mh square by 6. This is the moment of inertia possessed by the triangular section about the base BC now. In order to get the mass moment of inertia of triangular section about the central axis, we take it. This is known as the central axis. Here, by using only Parallax Theorem, according to the Parallax Theorem, IAB is equal to, that is IAB is equal to Ig plus mass into square of the distance between them is required. The position of the centroid is always at a distance of h by 3. Imagine this is nothing but equal to h1 now. So, From this relation now, h1 square, from this relations, Ig is equal to IAB minus of mh1 square. By using the relations IBC is equal to, already we got it is equal to mh square by 6. So, minus of m is equal to mass, h1 is equal to h by 3 whole square, that is mh square by 6 minus of mh square by 9, which is equal to mh square by 18. It is the mass moment of inertia of rectangular plate about its centroidal axis. Mass moment of inertia of the cone about the z-axis, which is perpendicular to the axis of rotation. Now, here we are taking a right circular cone now. Having capital R is representing the radius of the base circle now. Here the axis is kept to R dental now, and this axis is represented as x-axis as shown in figure now. The line which is passing through the vertex of the cone and perpendicular to the x-axis is known as here now y-axis. Now let us now to determine mass moment of inertia of intersections about the axis of rotations. That is the we required about the axis we required. In order to determine these values, first of all consider a small ring having thickness is equal to dx at a distance of x from the apex as shown in figure. The radius of the circle is equal to, here it is represented as a small r now. Now, according to the principle of geometry now, according to this one, I am writing this in the form of orthographic projections. I am taking only half of the cone like this, it is then like this. This is the representing capital R, this is representing small r, it is a O, if it is a B representing, it is a B, and this middle point is I am taking it is a A now, like this, I am taking, this distance is given, it is equal to x, so this distance is given, the length of the cone now. Now, according to the principle of geometry now, we are having R by x is equal to capital R divided by length, it is represented here h now, and so we are taking h values. From this relation, so R is equal to R by h into x. This is the equation number 1. Hence, we have taken R is equal to R by h into x now. The moment of inertia of circular lamina about the axis, x-axis, since it is passing through the centroid of the circle, and it is in the form z-axis there now, which is equal to mr square by 2. So, where m is equal to mass of the element, r is equal to radius of the circle now, which is equal to mass is equal to volume multiplied by the density, or area multiplied by the thickness multiplied by the density, which is equal to rho into area into thickness into square of the r square by 2. From this relation we got to rho into area is equal to pi r square and the thickness is equal to dx into r square by 2, rho pi r square x dx by 2 now. Since r is equal to r by h into x, and substituting the values we got to 1 by 2 into rho pi into r to the power of 4 divided by x to the power of 4 into x to the power of 4 into dx. So, the mass moment of inertia of entire solid cone about the axis of rotation, that is the x-axis, is obtained by integrating the above equation from 0 to h, that is ix is equal to 1 by 2 into rho pi r to the power of 4 divided by x to the power of 4, limits from 0 to x to the power of 4 into dx now. So, it is equal to 1 by 2 into rho pi r to the power of 4 by x to the power of 4, x to the power of 5 by divided by 5, and the limits from 0 to h, and substituting the limits 0 to h and the equations we got to 1 by 2 rho pi r to the power of 4 into h by 5 now. This equation I am rewriting in such a way that the volume of the cone is equal to 1 by 3rd pi r square h now. That is 1 by 3 pi r square h the volume multiplied by the density, that is nothing but equal to the rho. This is called here now mass. Since here dividing, just here multiply now. Again r square divided by 10 now. This is known as volume of the materials now. And so Ixx is equal to, I can take it as Ixx is equal to, this is equal to mass, this entire area, into 3 by 10 r square, or 3 by 10 mr square. This is representing the mass moment of inertia of right circular cone about the axis now, or axis of rotations. Okay, based on these equations, we can solve simple problems. If we know the length of the axis as well as the radius of the base circle. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.